Hello friends, today is the sixth part in the chapter alcohols, phenols and ethers. In our last sessions we have studied about alcohols and phenols. Today we shall see the final part, ethers. Ethers are organic compounds with general formula ROR dash. We shall now define what ethers are. Ethers are the organic compounds in which one of the hydrogen atom of an alkane is replaced by alkoxy group or aryl oxy group. What is alkoxy group or aryl oxy group? See, if this is the simplest alkane methane, I will remove one hydrogen from it. I have removed one hydrogen from it, and if the same is replaced by an alkoxy group, here it is methoxy group, or else if the same alkane has lost one hydrogen atom and in its place you replace by aryl oxy group, this group is aryl oxy group, then such compounds are called ethers. So ethers are organic compounds in which one hydrogen atom of an alkane is replaced by either alkoxy group or else by aryl oxy group, alkoxy or aryl oxy group. So these compounds are called ethers. Ethers are generally represented by the general formula ROR dash, where this group could be alkoxy or it could be aryl oxy group. It could be either alkoxy group or aryl oxy group. Let us see how these are classified. Ethers are classified into two types. One, based on the nature of this R group, if it is alkyl group or if it is aryl group, based on these they are classified into two types. One is simple ethers, one classification is simple ethers and the other is mixed ethers. If on the ethereal oxygen bond on the either sides, if both the alkyl groups or aryl groups are same, then we say they are simple ethers. For example, if one side you have CH3 and if the other side also you have CH3, then it is an example for simple ethers. If in ethers on the ethereal oxygen, if on the either sides both the alkyl or aryl groups are different, they are not same, then we call they are mixed ethers. Example, if one is CH3 and if the other is ethyl group, both the groups are different, then it is mixed ethers. If one side you have methyl group and if on the other side you have a benzene ring, then it is mixed ether. If one side you have ethyl group and if the other side you have ethyl group, then it is a simple ether. If on both the sides you have benzene ring, or if on both the sides you have benzene ring, then also it is simple ether. So simple ethers are those in which the alkyl groups or the aryl groups on either sides of the oxygen atom are same. Simple ethers are sometimes called symmetrical ethers also. They are also called symmetrical ethers, whereas mixed ethers which contain alkyl or aryl groups different on the either sides of oxygen atom, they are otherwise called unsymmetrical ethers. They are called unsymmetrical ethers. So how are ethers classified? Ethers are classified into two types, simple and mixed. What are simple ethers? Simple ethers are those in which the two alkyl groups or aryl groups on either sides of oxygen atom are same. In mixed ethers, the alkyl or aryl group on either sides of oxygen atom are different. Then now we shall see how they are named. The nomenclature of ethers is quite very simple. Let us begin with the simplest example. one compound which is derived from methane. I did say that from methane, if you replace one hydrogen and if the same is replaced by a simpler alkoxy group, then what should be this compound called as? So before I give you any example, let us know how they are classified. So ethers are classified into two systems, common naming system and IUPAC system. Let us see some examples for them and understand. In common naming system, the names of ethers are given based on the alkyl groups. Say if this is one compound, then its name in common naming system is given based on the names of alkyl groups. That's all. This group is called methyl, this group is called methyl. So if it has appeared twice, then the name should be dimethyl and the name will end as ether. As easy as that. So in common naming system, the names of ethers are derived from the names of alkyl groups attached on the either sides of oxygen. Whatever the names are, they are written. If the two alkyl groups or aryl groups attached on the oxygen atom are different, then whichever alkyl group comes first in alphabetical order, it should be written first. Like in this example, see H3O CH2 CH3. This group is methyl, this group is ethyl. So you cannot write the name as methyl, ethyl, ether. Which alkyl groups comes first in alphabetical order? This group. So ethyl, then comes methyl, then last final name is ether. Ethyl, methyl, ether. This is in common naming system. So in common naming system, the names of ethers are derived from the names of alkyl groups which are attached to the oxygen. If the alkyl groups are attached to the oxygen atom are same, then their names are not repeated. Instead, prefixes like di, tri, tetra, etc. they are used. If the names of alkyl groups are different, then whichever alkyl groups comes first in alphabetical order, that should be written first. How are they named in IUPAC system? In IUPAC system, they are considered as derivatives of alkanes. Which derivatives of alkanes? Alkoxy or aryloxy derivatives of alkanes. For that reason, the name of this compound is written as. See, earlier this was methane, because from methane you removed one hydrogen atom and replaced it by alkoxy group. So if this is methane, then this group is methoxy. It is an alkoxy group. In IUPAC system, ethers are called alkoxy alkanes or aryloxy alkanes. For that note, this compound is, this much is methane because one hydrogen is lost and the group should be attached as a prefix, then this group is methoxy. So methoxy methane is the IUPAC name. For the next compound, how do you write name? There are two possibilities. One, sir, if I consider this as parent and this as a substituent, then its name will be methoxy ethane. There is another possibility. I consider this as parent and this as substituent, then ethoxy methane. Which one is the correct name? Always remember, the bigger alkyl group is considered as parent. The smaller alkyl group is treated as a substituent. Therefore, methoxy ethane is the correct name. Methoxy ethane is the correct name for this compound. Another case, CH3 CH2O CH2 CH3. Now in this case, on either sides of oxygen atom same groups are there. So it is an example for simple ether. The second one was mixed ether. Now this group is ethyl, this group is ethyl, it has appeared twice, so di-ethyl ether. For IUPAC name, 2 times same groups, one becomes prefix ethoxy ethane because the parent has 2 carbon atoms in it. Then CH3O, this time 3 carbon chain on the other side of oxygen. So one side you have methyl, the other side you have propyl. So methyl, since it is a straight chain, therefore N-propyl ether. Methyl N-propyl ether. IUPAC name methoxypropane. It is methoxypropane. These were simpler examples. Now let us complicate a bit. You write the same methoxy as it is. Instead of 3, you write 2 chains and 1 carbon on the second carbon. Now how will you name this? One side in common naming system, one side you have methyl group, the other side you have isopropyl group. Therefore methyl isopropyl ether is the common name. Now some of you might have this doubt. Sir, you said the names of the groups should be written in alphabetical order. If that is true, then M does not come first because it begins with iso. The name should have been isopropyl methyl ether. Remember, N, iso, neo, all these are not considered while naming compounds in common naming system. Its group is propyl. So P comes after M. So do not get confused with respect to iso and N. So the correct name is methyl isopropyl ether only and not isopropyl methyl ether. Now in IUPAC system, numbering is done. Numbering is done in such a way that you are including the functional group as well as the longest chain rule is retained. So this time you have methoxy group attached to second carbon, therefore 2 methoxy propane. How did propane come? 1, 2, 3 carbons. So 2 methoxy propane is the correct name and not simply methoxy propane. Now after these nomenclature examples, we shall see structure of ethers. So in structure of ethers, why this is important means, we generally write ethers as ROR dash, where R and R dash may be same or different. If they are same, we call them as symmetrical ethers. If they are different, we call unsymmetrical ethers or mixed ethers. If I consider R as CH3 and this R dash also as CH3, then structure wise it is written as in this fashion, and this is wrong method. Ethers are not linear molecules. They are not linear molecules, they are bent molecules. They are bent molecules. Since ethers are bent molecules, this bond angle is looking like tetrahedral, but it is slightly more than tetrahedral angle. Its bond angle is 111.7 degree, which is slightly more than 109.5 degree tetrahedral angle. Because it is an angular molecule, ethers are not linear molecules, ethers are angular molecules. Why are they angular? It is because of the repulsions of the electron pairs of oxygen, the 2 bulky groups presence. For these 2 reasons, ethers have got angular shape. Because of angular shape, ethers bond angle is 111.7 degree. Now you say whether they will have zero dipole moment or net dipole moment. If I ask you to draw dipole moment, you will draw one dipole in this fashion, the other dipole in this fashion. Okay, whichever electronegative atom is there, the head of the dipole should be pointing towards that atom. So if this is true, then you tell whether it has got zero dipole moment or some net dipole moment. Yes, it has got net dipole moment because the two dipoles travel upwards. They travel upwards. If they were traveling in the opposite directions, then they would have cancelled their effect. Because both of them travel in the same direction, their net dipole adds up. Their net dipole adds up. Therefore, we say that ethers are polar molecules. Their polarity is because of this bond. Their polarity is because of this oxygen carbon bond. Since CO bond is polar bond and also the molecule is angular, therefore they will have net dipole moment, and their dipole moment is not zero. You cannot say they are non-polar molecules. Who are non-polar molecules? Those molecules which are linear, which are symmetrical, they are usually non-polar molecules. So even though we have a symmetrical molecule of ether, but because of their different bond angles, and bent shape or angular shape, they have net dipole moment. Okay, now let us study their methods of preparation of ethers. The first method is a very important method and most oftenly asked in the exams. It is Williamson's ether synthesis. This is also one of the hot favorite question that the question paper setter would like to ask. So in this method, you take alkyl halide, react it with sodium alkoxide or potassium alkoxide. If I choose sodium alkoxide is RONA. For my convenience, I will write it as NaOR. If not, you rephrase this equation as, first take sodium alkoxide, react it with alkyl halide. Then what will you get? You eliminate Na and X. Sodium halide goes away, leaving behind only ROR, which is an ether. So this method was devised by or given by Williamson's. Therefore, this method is called Williamson's ether synthesis, in which an alkyl halide is reacted with sodium alkoxide or potassium alkoxide, which will give you ethers. One example, CH3ONA plus CH3Cl. The product will be dimethyl ether with sodium chloride. Always remember, if you want to prepare unsymmetrical ethers, then the sodium alkoxide group should be larger one. You should select such that this group is larger and the alkyl halide is a smaller one. For example, if I wish to prepare any sol, what should be the reactants? So select bigger alkoxides and smaller alkyl halides. ONA. So Na and Cl will go, leaving behind OCH3, that is anisole or phenyl methyl phenyl ether. What the other product is? NaCl. So this is one method, Williamson's ether synthesis. Now we have second method also, that is by dehydration of alcohols. This one is also an important question for 3 marks. Nowadays it is not asked in theory exams, but it is important in competitive. The second method is by dehydration of alcohols. So if an alcohol is dehydrated, if it is dehydrated in the presence of a dehydrating agent like concentrated sulfuric acid at a temperature of 140 degrees Celsius. Specifying the temperature is important in this method. Why? I will tell you after some time. So if it is done, you will have ethers. You will have ethers along with dehydrated product, that is water. So use 2 molecules of ethanol. To explain how this happens, let us select one example. Use ethanol. When ethanol is dehydrated under same conditions, that is concentrated sulfuric acid and at a temperature of 140 degrees Celsius, then what is obtained? You should get ethoxyethane or diethyl ether along with water. You get diethyl ether as the product. Diethyl ether is the same ether that we use in many named reactions like Wurtz reaction, Wurtz fatigue reaction, preparation of Grignard reagents, and whenever Grignard reagents appear we write dry ether. It is this reagent, diethyl ether. How is it prepared? It is prepared by dehydrating ethanol at a temperature of 140 degrees Celsius using which dehydrating agent? Concentrated sulfuric acid. It has got mechanism which can be asked for 3 marks. So from alcohols chapter you have 2 mechanisms. One is dehydration of alcohol into alkenes. The second is dehydration of alcohols into ethers. So in the first step, you imagine that sulfuric acid has already donated a proton. Sulfuric acid being a dehydrating agent, it has now donated a proton. So our main reagent ethanol in the first step gets protonated. So this proton adds on or attaches itself to alcohol. So you will have CH3, CH2O, H was already there. Now one H got attached, one hydrogen got attached to oxygen. Since oxygen cannot tolerate 3 bonds, so positive charge. Now we call this is protonated alcohol. In the second step, a nucleophilic attack takes place. Means the second molecule of ethanol now attacks first molecule of ethanol, which is now in the form of protonated alcohol. So I will write this as CH3, CH2O, H, here also H. This was positive charge. Okay. Now this ethanol is attacked, protonated ethanol is attacked by a nucleophile that is normal alcohol. So when this ethanol attacks the carbon of protonated alcohol, this part goes away. It goes away in the form of what? HO as water. So water is removed and what is left behind? CH3, CH2O. I will write this H below, then dash CH2, CH3. Most of the students do the mistake of attaching CH3 first to this oxygen. No, you see this oxygen is attaching itself to the second carbon. So second carbon should be written here, followed by the first carbon. Again oxygen carries positive charge. The same positive charge is transferred to oxygen and loss of water takes place in the second step. In the first step what happened? The first step showed us that a proton from sulfuric acid is attacking ethanol and it is becoming protonated alcohol. The protonated alcohol is now attacked by a nucleophile ethanol to give you protonated ether. In the last step, this protonated ether, that is dimethyl ether, now should lose a proton. It should lose a proton. How does this happen? You see, oxygen is carrying positive charge. To neutralize, to balance this positive charge, the electrons of this bond, OH bond, transfers here on the oxygen to neutralize this positive charge. As a result, this H plus will go along with the positive charge as H plus. The same H plus which was generated in the first reaction is now regenerated. Now what is left behind? It is our main required product CH3, CH2, O, CH2, CH3, diethyl ether as the main product. So second method is also important along with the first method. Williamson's ether synthesis involves preparation of ethers by using sodium alkoxide or potassium alkoxide with an alkyl halide. Whereas in the second method, you carry out dehydration of alcohols at a temperature of 140 degrees Celsius using dehydrating agent 200 degree, using dehydrating agent concentrated sulfuric acid. This will give you ethers. Now I did mention why mentioning the temperature, why keeping the temperature 140 degrees Celsius is essential. So if the dehydration reaction of alcohols is carried out at higher temperatures, say 200 degree, if the temperature crosses 200 degrees Celsius, if the temperature crosses 200 degrees Celsius, then you will not have ethers, you will have alkenes as the product. So if you want the product to be an ether, then maintain the temperature at 140 degrees Celsius. If the same reaction of dehydration of alcohols is done at 200 degrees Celsius, then you will end up with alkenes. This is one note to be remembered in the second method by dehydration of alcohols. If the same reaction is carried out at 200 degrees Celsius, then alkenes are obtained. Then second note is, it is suitable for preparing, this method, second method is suitable for preparing ethers which are simple and which have only primary alkyl groups. Those which have secondary and tertiary alkyl groups, such ethers cannot be prepared by this method. If that part is clear, now we shall go to the physical properties of ethers. Under physical properties, I always tell you that the first property is usually their physical state. So when it comes to physical state, the first property is dimethyl ether, which contains only 2 carbons, and ethyl methyl ether, 3 carbons. So the first property is dimethyl ether and ethyl methyl ether. Only these 2 ethers are gases. Only these 2 are gases. Rest of all the ethers are liquids. They are all liquids. What kind of liquids? Colorless liquids, but highly volatile liquids. They have some pleasant odor. They are colorless, highly volatile, pleasant smelling liquids. So first property is, in the ethers, only 2 ethers, that is dimethyl ether and ethyl methyl ether. These 2 are gases. Rest of all the ethers are colorless, highly volatile liquids. Only the lower ethers smell pleasant. Then the second one, if you compare their boiling points with their alcohol members, compared to alcohols, ethers have low boiling point. Now if you have not forgotten, in the alcohols part, I did tell you that alcohols have got higher boiling point compared to their hydrocarbons. The reason was intermolecular hydrogen bonding. Such intensive intermolecular hydrogen bonding is not seen in ethers. Therefore, compared to alcohols, ethers will have lower boiling point. Ethers will have lower boiling point compared to alcohols. This means if I give you three compounds, a hydrocarbon, that is an alkane, alcohol and ether, which one will have the highest boiling point? Alcohol. Second comes ethers. The last comes alkanes. Why do ethers have low boiling point compared to alcohols? If this is your 1 mark question, your answer should be because of the absence of intermolecular hydrogen bonding in ethers. Ethers have got low boiling point than alcohols of corresponding molecular mass, not any other random alcohol. Same corresponding molecular mass alcohols, if you consider them, then their boiling points will be higher than that of ethers. Then the third property, I have told you about the structure of ethers. In ethers, we have bent molecule. So, ethers have net dipole moment. They have net dipole moment because of angular structure. Because of angular structure, ethers have got some net dipole moment and their dipole moment is not 0. The fourth one is, ethers are sparingly soluble in water. They are sparingly soluble in water. Sparingly soluble means less soluble in water. Now you can guess why they are sparingly soluble or less soluble in water. Because they do not form intermolecular hydrogen bonding. But they are fairly soluble. But they are fairly soluble in organic solvents. But they are fairly soluble in organic solvents. However, one point to be remembered is that lower ethers, sometimes lower ethers can be soluble in water because of hydrogen bonding. Do not get confused. See, this is one ether, this is another ether. We have two ether molecules. So, if water is available, so they can be soluble in water, but to a lesser extent. Ethers are sparingly soluble in water because of this hydrogen bonding. But if you compare their hydrogen bonding with alcohols, it is very less. So, compared to alcohols, ethers have low BP. That is true. It is true because they do not form intermolecular hydrogen bonding with themselves. Ethers cannot have bonding anywhere among themselves. For this reason, because of the absence of intermolecular hydrogen bonding, their boiling point is low compared to alcohols. Do not get confused with this with the solubility. When it comes to solubility in water, you have water for forming hydrogen bonds. So, this hydrogen bonding is shown by only lower members of ethers. So, lower members of ethers are soluble in water, that too sparingly. Very less soluble in water because they show slight intermolecular hydrogen bonding. However, as molecular mass increases, as number of carbon atoms increases, as the alkyl group chain increases, solubility decreases. They are however soluble in organic solvents. Then the last property is, lower ethers are used as anesthetic agents. They are used as anesthetic agents. You should be knowing what anesthesia is. Anesthesia is the procedure of making a patient not to feel pain while he is being operated upon. So that is anesthesia. For doing anesthesia, earlier chloroform was used. Now because chloroform is considered to be dangerous, the chloroform is now replaced by ethers. Ethers are now used as local anesthetic agents. So these were physical properties. Now let us see their chemical properties. There are very less number of chemical properties for your syllabus. The first chemical property we shall be studying today is cleavage, means breaking. Cleavage of CO bond in ethers. Where is the CO bond in ethers? Ether general formula is ROR. So where is CO bond? So if this R is CH3, if the other R is CH3, then you can have CO bond. Then you can have CO bond. So how does this bond break? So one example, whenever ethers react with an acid, hydrogen halide, then you will have this much part you separate. What is left? Alkyl halide and ROH, alcohols and alkyl halide is obtained. In this way, the bond between carbon and oxygen, ethereal bond, can be broken. Further, these two, out of these two, this alcohol ROH again reacts with hydrogen halide to give you second molecule of alkyl halide and water. In the first step you got alcohol as a byproduct. In the second method you got water as a byproduct. The same we study in one of the chemical properties of alcohols also. That is, if this HX is HCl, then we write here anhydrous ZnCl2. Its mixture is called Lucas reagent, which is used to identify three different types of alcohols. So remember, whenever ethers are reacted with hydrogen halide, the bond between carbon and oxygen breaks to give you alkyl halide in the first step. In the second step, the byproduct of the first step, that is alcohol, again reacts with hydrogen halide to give you second molecule of alkyl halide. If this is understood, then now you tell me what should be the product if dimethyl ether is reacted with HCl. It should be CH3Cl plus CH3OH. Using this byproduct, if the same again is reacted with this HX, what should be the product? CH3X plus H2O. Simple. Now let us see the main example that is frequently asked in the exam. If anisole is reacted with hydrogen iodide, what should be the product? It should be OH plus CH3I, or else should it be I plus CH3OH. This needs very perfect understanding of these two reactions. So whenever anisole is reacted, these two go with each other to give you phenol as the main product. This reaction is not possible. This is asked frequently in the exam as what happens when anisole is reacted with HI? Give equation. Writing the statement that phenol is obtained carries 1 mark, and writing the same equation carries another mark. So it is a 2-mark question. Do not get confused. Anisole upon reacting with hydrogen iodide gives you phenol and not iodobenzene as product. The second chemical property. The second chemical property is electrophilic substitution reaction. Electrophilic substitution reactions. In order to understand electrophilic substitution reactions, you should have a sound idea of resonance structures. So if I use an aryl oxybenzene, that is unsymmetrical ether, then you know that this group I can replace R by CH3. Methoxy group is an electron donating group. So if it donates electrons to the benzene, I will replace for convenience as R only. If it donates electrons to benzene, then The subsequent resonance structures are as seen on the board. Because oxygen has lost electrons, I will write positive charge here. The same negative charge appears outside. This delocalizes again. So, the next structure we have here, double bond OR plus, here bond, here minus charge. The minus charge again travels, therefore minus charge here, OR plus charge, this appears here, and the same double bonded character shifts finally to give you the last resonance structure, that is OR. You again got the same product. Now why did I write resonance structures? You know what an electrophile is? An electrophile is the one which donates electrons or accepts electrons. It accepts electrons because it is electron deficient species, and it likes to attack those places which are rich in electrons or where there are more electrons. For that reason, if you write resonance structures, you will be able to identify that the negative charge appeared at ortho position, again at para position, and finally again at ortho positions. So this group, that is alkoxy group, OCH3 or OR groups, these are electron donating groups. They are electron donating groups. Because of presence of an electron donating group, it donates electrons to the benzene ring, making it an electron rich center. Therefore electrophiles can attack easily. Now you tell whether anisole should undergo electrophilic substitution reaction or not. Yes, it will undergo electrophilic substitution reaction because of the presence of methoxy group, OCH3 group. Now when it undergoes electrophilic substitution reaction, what should be the products formed? The incoming electrophile can attack which two places? It can attack either ortho position or para position. Therefore in all the subsequent reactions that you will study, wherein the products are two, one is an ortho product, the other is para product. Which one do you think should be the major product? Always para product is a major product because it is far away, from the electron donating group. Now let us see the first electrophilic substitution reaction. It is nitration. It is nitration. For nitration you choose anisole, react it with nitric acid, in the presence of sulfuric acid. So you should have two products. Those two products should have same methoxy group undisturbed, but you should attach nitration reaction part is nitro group, once at para position, the other time at ortho position, followed by water. 2 molecules of water, so 2 molecules of HNO3, 2 anisole. So whenever anisole is nitrated, you have para nitroanisole and ortho nitroanisole as the products, out of which one is major? Para is major. If the same reaction is done for halogenation, if it is done for halogenation, again same anisole is reacted with bromine, then you will have OCH3, here Br plus OCH3, here Br plus 2HBr. So two products, ortho-bromoanisole and para-bromoanisole are obtained. For the third time you carry out Friedel-Crafts reaction. Under Friedel-Crafts you have two, one is alkylation. For alkylation what do? You react anisole with methyl chloride in the presence of anhydrous aluminum chloride. What is the product obtained? You will have OCH3 as it is, here CH3 once at ortho position, the second time it is at para position, plus HCl. 2HCl, 2-methyl chloride, 2-anisole. In Friedel-Crafts alkylation, alkyl group is substituted and this product is called orthomethoxytoluene, paramethoxytoluene. If the same is done for acetylation, acetylation means you need same anisole with acetyl chloride under same anhydrous AlCl3 as a catalyst or halogen carrier. The products are OCH3 as it is, COCH3 is substituted, OCH3 as it is, here COCH3 plus 2HCl. Here you got toluene. Which toluene? Orthomethoxytoluene and paramethoxytoluene were obtained, out of which paramethoxytoluene was major product. Here you will get acetophenone. COCH3 is acetophenone group. So which acetophenone? Paramethoxyacetophenone is obtained as major product along with orthomethoxyacetophenone as a smaller product. So today we studied in ethers, their definition, their nomenclature, their classification, structure of ethers, methods of preparation, physical properties and chemical properties of ethers. Thus we have concluded the chapter alcohols, phenols and ethers. In our forthcoming sessions we shall see and begin a new chapter. That's all for now. Thank you.